Hello, everybody, and welcome to another Saturday Morning Physics. It's my pleasure today to welcome and introduce James Wells, who is a professor of physics and at the Lineweber Center for Theoretical Physics here at the University of Michigan. James was a graduate student here actually at Michigan. He did his graduate work with Gordy Kane and received his PhD in 1995. And then he did postdoctoral work at Stanford, and he was a fellow at CERN for a year before becoming an assistant professor at the University of California, Davis. Then actually we had the opportunity to bring him back to the University of Michigan in 2002, and he's been a member of the faculty here ever since, rising to the rank of professor in 2008. But he was also a staff scientist at CERN from 2007 to 2013. Professor Wells does research in theoretical physics addressing the deepest questions, including the origin of mass, the origin of gauge symmetries, flavor violations, CP violation, and dark matter. He's a fellow of the American Physical Society. He was the recipient of the Outstanding Junior Investigator Award from the Department of Energy, and a Sloan Fellow from the Alfred P. Sloan Foundation, and also received a Humboldt Research Award in 2016. He's also a fellow of the American Association for the Advancement of Science. In addition to his research in elementary particle physics theory, he served as a member of the HEPAP panel. That's the High Energy Physics Advisory Panel, which advises the funding agencies, Department of Energy and the National Science Foundation on the status and direction of high energy physics research and funding. And most relevant to his discussion today, he's a member from 2013 to 2020 of the panel on public affairs of the American Physical Society, and he was chair for 1 year, and he spent another year as a chair of a subgroup on national security. And so he brings us today his expertise in science policy, and his lecture is entitled On Deciding the Next Big Science Experiments. Welcome, James.
Nice introduction. It's all good. Okay, I should do it higher. All right. Yeah, so today I would like to talk to you about deciding the next big science projects. It's much more than science. It's much more than just science. This talk is similar to a talk that I give to physicists. And it's slightly different emphasis. Here I will be doing a little bit more of the big picture aspects. Physicists sometimes want to know a little bit more about how the sausage is made. And I got to see that for several years in the HEPAP panel for DOE. But I think, and I hope that this will be of interest to you on the issues that science faces, that society faces, when deciding on a very large-scale science project. And by a large-scale science project, I don't just mean cost, although cost is usually the clearest earmark of that, but also the impact it has on the big picture, so to speak. Maybe one could say it very efficiently as what might be in the New York Times. And so this is the discussion that I would like to have today. The left picture here is associated with the Aegis ballistic missile defense system. And I'm going to use that as an example of a big experiment, a big test that was done recently and the issues that went behind that. And on the right is a picture of the CMS detector at CERN. That's another big project that happened. But there is a future collider project called the ILC that I will discuss as an illustration of the decision-making process for the next generation experiments in particle physics. Okay, let's start with the Aegis system. This is a press release from the Department of Defense on November 17th last year, so almost a year ago. The U.S. Missile Defense Agency and U.S. Navy sailors aboard the USS John Fenn, an Aegis ballistic missile defense system-equipped destroyer, intercepted and destroyed a threat representative intercontinental ballistic missile, or ICBM, target with a Standard Missile 3 and SM-3 Block 2A missile during a flight test demonstration in the broad ocean area northeast of Hawaii on November 16th, the previous day. This is a picture of what that test was to look like. Off in the ocean on a small island, an ICBM class target was launched, and radars picked it up. It was tracked, and then aboard the USS John Fenn, an Aegis system destroyer, the SM-3 Block 2A missile was launched and intercepted this ICBM target. This was a test a long time in the planning and delayed somewhat because of the COVID problems. So this test was the first experiment, major experiment, one might say, to assess the Aegis ICBM intercept capability for the layered defense concept. So this is a picture from the Department of Defense. This is an ICBM coming on red. And then we have a system deployed already called the Ground-Based Midcourse Defense System. There's some interceptors in California, but most are in Alaska. So a missile, for example, coming from North Korea comes out from the north towards the United States, and this system is supposed to intercept that. But there has been some difficulties with that system, which we'll mention a little bit later. And so a new possibility of equipping these destroyers with ICBM intercept-capable system would be put behind it as an underlay to this GMD system. And then yet a third system, which is much further away from deployment, is the THAAD system. That we won't mention any further. It just happens to be on that on this slide. But this is much, much further in the future than a potential Aegis intercept system. So this was a test to see if if it really could be an underlay to an ICBM protection. This was the comments immediately after that test by the Vice Admiral John Hill, who is the director of the Missile Defense Agency. This quote what he said: "This was an incredible accomplishment and critical milestone for the Aegis BMD SM-3 Block 2A program. The department is investigating the possibility of augmenting the ground-based mid-course defense system." That's what I was showing on the previous slide. "We have demonstrated that an Aegis BMD-equipped vessel," that's that USS John Fenn, "equipped with a Standard Missile 3 Block 2A missile, can defeat an ICBM class target, which is a step in the process of determining its feasibility as part of an architecture for layered defense of the homeland." Now, 6 months later, there was a report from the Government Accountability Office, which has an augmented and a more reviewed response to that test. And they say that achieving such a capability, intercepting an ICBM, will require surmounting several challenges. According to the MDA, the Missile Defense Agency, during that November 2020 test, the SM-3 Block 2A struck a simple ICBM target. This was not an operational test, however, and it was executed under highly favorable conditions. More development work is needed. MDA documents show that the agency now plans to develop and procure an upgraded version of the SM-3 Block 2A for the purposes of fulfilling this homeland defense mission. So much more work needs to happen. The SM-3 Block 2A performance is, if you read between the lines, is not entirely adequate for the job. The test was done under scripted circumstances, which is expected in a first major test like that. And full system integration and tests in realistic circumstances are needed to show that it is effective. So this experiment or test, depending on the language you prefer to use, can be described as a simple technical question that might come up in a meeting among military officials and congressional officials and administrative officials. Let's determine whether an SM-3 Block 2A missile can intercept an ICBM class target. So that's a straightforward question. It's a technical question. And only a scientific technical study can answer that question. It is a well-defined question. The experiment is well-defined task without much ambiguity. I put a star next to ambiguity because this question of whether or not the test indeed is indicative of the ability to intercept an ICBM class target is important and constitutes a non-trivial ambiguity. But from the purposes of a straightforward kinematic intercept, it can be described simply. It's not a wacky idea. So when you propose new experiments, if you have what we colloquially might call a wacky idea, you will have a lot of difficulty convincing people that it is the right thing to do. The burden of proof that it is an acceptable experiment to do, that it is a worthwhile experiment to do, is much higher. This activity is similar to other activities that have been done in the past. There are scores of missile defense tests that have happened within the military, including the ground-based intercept tests, which are devoted towards determining if we can intercept ICBMs. There are many other missiles besides ICBMs that one has to worry about and one might want to intercept. ICBMs are the toughest ones. They go the furthest. They are the fastest. They are the most powerful, and they have strategic implications, existential implications for countries on the receiving end. So tests against ICBM intercepts have been happening many, many times. So this is an idea that is not wacky, as one might say, to do it. It is affordable in the scheme of defense projects. It may be considered affordable. Other tests in the GMD systems were certainly comparable, if not more expensive. So this is an affordable test. And finally, it's a forefront test. It's a severe technical challenge. It's coordinating radars, tracking, computational elements, personnel abilities to carry out all the procedures accurately in a very short period of time, to have all these elements coordinated, combined with the performance of the intercepting missile to begin with, which required years of background work. So this pushes the envelope. So all the scientists, when I give a talk like this in front of scientists, they recognize all four of these elements as really crucial elements for designing an acceptable experiment that might get funded and might be worthwhile. And so it has all the earmarks of an excellent experiment to do within the realm of national defense. After all, it is just asking a question and trying to answer a question. There is no nuclear radiation involved. The ICBM flew over the Pacific Ocean in a way that did not threaten anybody. It was not an nuclear-armed ICBM. It was a mock target, and it's just a straightforward technical experiment to do. And as scientists, one might just say, yes, let's do it, because it's an interesting question also. Whether or not these new missile types, the SM-32A, really have the performance capability of intercepting an ICBM. However, there is one category in decision making which was really the overarching question. And sometimes it is stated explicitly, and sometimes it's implicit, and sometimes it's not asked at all. And the question is what I would call the core value question. Does the activity increase value overall to the well-being of citizens? So every single public-funded project needs to address this question. And it needs to be serious about addressing that question. Now, value is a really difficult part of this to answer. Every single person in this room has a unique set of values. And it's surprising that we are able to cooperate enough even to build this auditorium with every single one of us having a different set of values. So it becomes a tricky question to ask what has value overall to the well-being of citizens. But one must address it, and one must discuss openly and extensively, especially questions which involve very large public investment, taxpayer investment. This is a key question. If you were doing something out on the diag that costs $72.32 to do a little experiment, we don't have to talk too long about that as a society, but other things we do. Now, maximizing value with finite resources is an extremely hard question. In fact, maybe an impossible question. Anytime you involve the word maximizing, you know that life will be very difficult in answering that question. All the way from technical physics and engineering problems, even low scope problems, to the very largest questions. And as the questions get larger, maximizing value is, it's almost a theorem that it's impossible to know if you've done that. But even just guaranteeing value is hard enough sometimes. And especially when there are many moving parts to the questions involved. So in the national defense and national security realm, we can simplify the question. We can simplify the question to, does the experiment test have value by overall increasing the safety and security of citizens? Answering that question requires a lot more knowledge than the physicists and engineers and computer operators involved in the particular experiment itself. And I want to discuss that a bit. So let me give you some background behind this test, okay? And it's only a small sliver of the background. North Korea in 2017 successfully tested Hwasong-15 ICBM that has the capability of carrying nuclear weapons to US territory. And this test was all done within an environment that included threats from multiple sides, heated rhetoric, and uncertainty in North Korea command and control structures even. So the worry about protecting the homeland from ICBM threats coming from the North was very much on the minds of people, especially after North Korea finally demonstrated its ability to field an ICBM class missile. Furthermore, the U.S. has deployed, as I mentioned before, the ground-based missile defense system, the GMD system, but it was deemed less reliable than originally hoped for. There were so-called kill vehicle problems. Now, what that means is that the missile associated with the ground-based missile defense system does well and is on a trajectory towards intercept, but an ICBM's motion is not as simple and as fluid as one might hope if you're trying to defend against an ICBM. So what happens is you have to release at the very last moment a kill vehicle. And the kill vehicle has to have its own thrust and its own high maneuverability to make the final close-in for a kinetic kill on an ICBM target. The exo-atmospheric kill vehicle that was originally part of this had some problems. There was a redesigned kill vehicle program that was put in place that was meant to rectify the issues. And by problem, I mean that the reliability was not as high as they wanted it to be to feel safe. So there was a redesigned kill vehicle, but that was canceled in 2019 by assessments that it could never reach the design criteria that we feel is needed. So then a new program was born for this final kill vehicle on the top of the interceptor. And this is the so-called next generation interceptor. And it's a restart on the kill vehicle design. And there's hopes for testing it in the mid-2020s and deployment in late 2020s. So this is years from now on deployment of it. The GMD system is still in place. There's still some reliability, but to get to the higher reliability associated with this final intercept, if they can accomplish it, will happen not until the end of this decade. So there was great need for something, an underlay to this system to help protect us in the face of this emerging threat. So now, in that context, we can think again about this core value question. And we can think about it as Congress might think about it, which is protecting citizens of the U.S. against catastrophic loss. So does everything that we do in this realm should be towards the goal of protecting citizens against catastrophic loss. And internationally, there is protecting global citizens against catastrophic loss. So what are the ways in which this test might contribute to this value? Well, that's kind of obvious. So we can determine if the SM-3 Block 2A missile can down an ICBM, and if so, its deployment for those purposes can be done to help cover for GMD, this ground-based missile defense system. And second, demonstrate to North Korea and others consistent U.S. resolve to countering ICBM threats with hopes that they will view their offensive efforts as futile. There are multiple other ways in which the tests might contribute to this value. I will mention later that the test might contribute to value to allies, not just to the United States, in particular Western Europe and Japan. So ways in which the test may not contribute to this value. There are myriad ways where the risks are there. So I have to remind you that this SM-3-2A is a high performance intercept, a higher performance intercept than the US had ever had before for this Aegis missile defense system. Some of you will recall that in the Obama administration, there was a new program developed, the European Phased Adaptive Approach, which involved fielding SM-3 missiles in Romania and in Poland in order to protect Western Europe and NATO allies against the possible threat of Iranian intermediate range missiles, not ICBMs, but intermediate range missiles. So those are lower, the original missiles involved with that. So for example, the SM-3 1B, not the 2A, but the 1B, they have lower performance, lower speeds, and they assuredly would not be adequate for intercontinental ballistic missile intercepts, which are much faster missiles that the 1B missiles could never intercept really effectively and reliably. So by fielding a new weapon with much higher performance capabilities, which this test was meant to demonstrate, it wakes up Russia and China as well. And it's not a passing wake up. It is a very serious wake up. It is serious enough that the Obama administration canceled the 2B intercept because its performance was going to be so high that it was clearly, and it seemed to be unmistakably geared towards ICBMs that could threaten strategic deterrence of China and Russia. And for most of the last 20 years, missile defense in the US, the policy of the United States was that it was not geared towards Russia and China. And mutual deterrence was the strategic value vis-a-vis Russia and China. Any fielding of missile defense capabilities that threatens the strategic arsenal of Russia and China becomes a very serious question in international diplomacy. And it has become a serious question. And it induces, potentially, and according to the Russians, assuredly, an offensive-defensive arms race that may create some further instability. Furthermore, improved defenses can lead to trigger finger of an adversary who believes that maybe the US is on the cusp of being able to completely protect itself against any of our threats. Therefore, we need to make it happen now before they have their redesigned kill vehicle finished and before they fully tested the Block 2A missiles. Another issue that the Navy brings up quite a bit is that it draws away crucial Navy resources for other activities that are necessary and therefore may induce additional risk and therefore possible loss. It can create dangerous confusion that improved strategic missile defense efforts may ultimately be for Russia and China, as I mentioned. So this missile that was used in the test last November is something that can also be fielded on the ground elsewhere as a defense against ICBMs from anywhere. And confusion within the US, this is also a key issue, confusion within the US of the effectiveness of missile defense capabilities. I can show you quotations from administration officials that have what we might view as an incorrect assessment on the reliability of missile defense. At the present, we do not have reliability against a Russian or Chinese ICBM. It's just simply the case, and nobody would deny that, who's in the technical realm of this. But we may have effective defenses against the less sophisticated forces of North Korea and a potential future missile of Iran. So just by doing the test and pursuing ICBM capabilities of the SM-3 2A yields strategic and international relations discussions, to put it mildly. Now, a report that just came out last week emphasizes something that we've heard the Russian President Vladimir Putin say many, many times, that the prospect of long-term threat to its forces through ballistic missile defense has led and prompted Russia to develop new exotic systems designed to ensure its retaliatory capacity. So the avant-garde boost glide, hypersonic boost glide vehicles, Poseidon long-range nuclear uncrewed underwater vehicles, and the nuclear-powered cruise missiles. But the ones that have been tested by Russia and now recently by China are these hypersonic glide vehicles, which are very adept at evading missile defenses that we have envisioned for the next, say, 20 years. So Russia, furthermore, has expressed significant reservations about any further cuts to its strategic offensive forces through arms control if missile defenses remain unconstrained. This is a very significant issue in arms control world, that missile defense and offensive weapons go hand in hand in arms control agreements. So this shows you that the trickiest question involving an experiment or a test is often not how to do the experiment or test, but whether there's even overall value in doing it. There are legitimate arguments that say this test was worthwhile to do, and legitimate arguments that say this test, that indicate this test might not be worthwhile to do. Again, expertise goes well beyond what is required to do the experiment, to do the test, and to assess this core value question. Are we safer by having done the test than not? And this involved the discussions that went on for months and even years, depending on how you interpret it, involved missile defense engineers, physicists, radar and remote sensing engineers, computer scientists, and many other technical expertises. Political scientists, there's a very major thread within the political science community that works on missile defense and offensive, defensive arms races. Economists, experts on Russian, Chinese, North Korean, and Iranian military strategies and capabilities. There's much more to say there. And this allies assessments. So NATO is paying very close attention. Our allies in NATO, our allies in the Pacific Rim are paying very close attention to it. Japan had an Aegis system. They co-developed, actually. The SM-3 Block 2A missiles was co-developed with Japan. Military officers in the Navy, very intensive discussions with them, administrative officials, and Congress. And after all those discussions, the result, do the experiment. It was congressionally mandated and put in law that this test had to happen. Okay, so that's the missile defense example of all the different issues that go into just deciding if you want to do that experiment. And let's do a second example. The second example is a new particle physics collider. The decision to build a new high-energy particle collider such as the International Linear Collider, the ILC. This is an electrons accelerated at extremely high energies, and positrons accelerated at extremely high energies, colliding inside some detector facility to see what happens. And the electron-positron collisions that would happen at the ILC has not happened yet. It is in the planning stages and the proposal stage. It would be from 2 times to 10 times past records set at CERN for electron-positron collisions. Japan has been the leader in the ILC program, and they, together with international partners, including the US, have proposed, scientists have proposed this collider. But the question that you must ask is, don't we already have a big collider? Yes, we already have a big collider. Why would we want to spend $10 to $20 billion on a new collider? And we have the Large Hadron Collider at CERN in Geneva, Switzerland, which is running right now, or I should say will run in a month or two again. And it will run for another 10, 15 years. The LHC, however, is a slightly different collider. It's a proton-proton collider at 14 TeV. So that 14 TeV just means an incredibly high energy that you can't do in your basement. So extremely high energies, proton-proton. The highest ever energy, and this is the ring at CERN. So it's 27 kilometers. And there's, you see Lake Geneva here, and this ring goes all the way around. And you need that big size of ring with the highest magnets that have ever been made for this purpose, the highest field magnets to accelerate these at the sufficient energy for, to make new things. And they found the Higgs boson at LHC, a smashing success, to use a nice pun. Now it restarts very soon, and so you have to ask, why do we want another collider? And there are many, many reasons. I'm going to boil it down just to one slide, because this talk is not to try to convince you that the ILC should be done, but to give you a flavor for why people want it to happen, and then all the issues that are involved in deciding it. Well, not all, but I can't keep you to 3 o'clock. So key physics reason given, this is probably the key one, is to understand exactly what this Higgs boson that CERN in Geneva, Switzerland found. Now this plot, there's many theories that suggest that you can see small deviations of the Higgs boson's decays into other particles. Let me come back to this slide, but I'm going to go one slide forward and then come back to that one. So these are all the different decays of 125 GeV standard model Higgs boson, and this is what they think they found at the LHC. And all evidence suggests that indeed we did find a standard model Higgs boson at 125 GeV. But you have to test it to see if it really is that. So a Higgs boson will decay into 2 bottom quarks 57% of the time. It will decay into 2 W's, WW star, 21% of the time, 2 gluons, 9% of the time, 2 tau particles, 6% of the time, and so on. And 2 photons, only 0.2% of the time. So there's lots of different things to test. And and others, there's a lot of stuff in others, a dozen other things in others. So the LHC discovered this by finding evidence through photon-photon and through ZZ, these two. And the reason, even though those are small branching fractions of the Higgs boson, it doesn't decay to it that often when it's produced. It was a good way to find it. But what we want to do, and they see evidence for it going into many other things, but the measurements have not been as precise as we want in order to fully test this theory. And as I say, there are many theories of the Higgs boson that tell you that you should have small deviations away from what the standard model tells you it is. And those small deviations are too small for the LHC collider at CERN to see. So this is precision of Higgs boson couplings to ZZ, WW, photon-photon, BB, tau-tau, all these different states. And in red is all this imprecision, or not super high precision, that the LHC will ultimately get to in maybe 10 years. So they'll never get better than this. But many ideas tell you you need to get down to here. So in Japan and the United States and elsewhere around the world, we wish to build an E+ E- collider, electron-positron collider, in order to get down to these green levels. So these green levels are where you have an ILC collider in addition to the LHC collider. So that's the main physics reason for it. Okay, so this is a bunch of physicists in a room somewhere saying we really want to learn this. And the questions go deeper than that. So in a physics lunch, many physicists will say, fantastic, we can learn so much to do it, let's do it. And and often don't want to talk too much more about other things. But the other things include, well, how much does it cost? And then that oftentimes comes with the phrase, don't do it if it's too expensive. So frequently, it becomes an argument within the physics community of the physics case, and then how much does it cost, and can it come under the bar of the total US spending on particle physics? So that's one way it's phrased in the physics community. When you go outside the physics community and you deal with Congress and you deal with citizens, there's a very different calculus that's involved. And it's a good calculus, in my view. So it's useful to step back and ask this core value question again. The core value question is, does the activity increase value to the well-being of citizens? Now, if I know better what this Higgs boson is doing, does that really increase the value to you? So that could be a tricky question. It's actually even more tricky maybe than a ballistic missile defense test, perhaps. There are many issues to think about, many issues that physicists do not think about, which I was forced to think about in Washington many times. And I want to tell you about some of those issues. And you probably, many of you in the audience will more naturally think about these issues than physicists do. You probably were more natural to capture some of these potential benefits and potential costs than a really excited physicist like me who just wants to build that thing yesterday, all right? So here are the potential benefits. Okay, so usually we don't go much further than, so in italics is what a physicist dominantly thinks, okay? Or when I say physicist, I say me some time ago. Deeper knowledge of nature, discovery. Okay, no reason to talk further than that. That's worth it all on its own, right? So that's how a physicist would think. But there's many more issues that people in Congress think about and other organizations. And they are surprisingly a long list that is very interesting to consider. For example, the employment of scientists. It is a national security issue even that the US has a certain level of employment of scientists for nimbleness in case of national security threats and so on. There's regional district employment gains that can make generations worth of difference by having a large-scale, coherent experimental facility in a region. It attracts young people to STEM. This is a potential benefit. It's a tricky benefit because if particle physics did not exist, would the number of young people going into STEM be the same, or would it decrease? It's unlikely it would decrease, but one could make a somewhat twisted argument that it might. So we have a difficulty in attracting young people to STEM. And in half the NOVA specials on physics are particle physics. And astronomy is almost the other half. So this is a big attractor to STEM. As I say, it's a buffer for US STEM positions through employment. There's regional enhancement due to the presence of a world-class facility. Something that's not terribly appreciated is if you spend $10 billion on a copy of something that somebody else did, but you can do a lot of work and you can do some good science experiments there and so on. The enhancement regionally and even nationally is not as great as if you do something unique. where all the scientists recognize that that is the only place and the best place, and everybody else is second fiddle. A state-of-the-art collider facility is a relatively straightforward, easy way to not be second fiddle overnight. And this is one of the reasons why China is taking significant interest in building a new high-energy particle collider. You attract the world if you have the top place. If you just do something standard and reproduce it somewhere, you don't attract the top people. I can go to Illinois and do that research. I don't have to go to Beijing. But maybe I do have to go to China to do the state-of-the-art particle physics experiment that nowhere else in the world could possibly do it. So this is a very important and understood by politicians that this feature. It's a global innovation hub. So we have faculty in our university who have studied the global innovation, regional and global innovation. There's economic returns on innovation and tech transfer, even in particle physics experiments. Something that has become extremely important of recent is some of the largest data sets in the world and the most sophisticated data processing is happening through high-energy physics colliders facilities. So you're training hundreds and hundreds of people at the very forefront of data science and data manipulation and artificial intelligence training to pull out these little signals in the midst of an unbelievable amount of violence happening inside of a collider requires formidable big data training and artificial intelligence training. Accelerator physics training and innovation, national prestige and confidence building. Sometimes I've talked to politicians, and this is not at the bottom of their list. This is a significant issue. Large-scale cooperation training, employment and training of large-scale civil engineering. From my discussion with colleagues in Japan, this is a significant issue. There's a national security issue and a national economic security issue of having a well-trained, large civil engineering corps, and especially the ability to do forefront things in the civil engineering side. And a significant cost of a collider facility is not a particle physicist doing their thing, it's civil engineering projects. And it is a government project to help sustain the country's civil engineering infrastructure. So the potential costs, in italics, this is what a physicist will immediately think of. There's a potential lost science discovery investment. These particle colliders are speculative in nature. We don't know if our understanding of nature will be revolutionized by a new experiment or not. And so in that sense, it's speculative. If we knew it would be revolutionized, then we wouldn't have to do the experiment, as the saying goes. It's also a big cost, $10 to $20 billion to do these forefront colliders. You can't do a $1 billion collider and get one-tenth of the value. If you do a $1 billion collider, you get basically zero value. You have to go all the way. And it's a big cost. And that big cost has several impacts. And most of the things underneath are related to that. Well, the first one is increasingly of interest to people, environmental impacts, the energy consumption involved. However, I think it should be energy consumption per STEM training is probably a good measure. Ineffective science innovation investment. So a common thought is that maybe we can seed innovation for the economy in more effective ways. That's connected to inefficient STEM training, cost per quality worker that enters industry. Most people who get trained in these forefront science projects do not just stay a particle physicist for the rest of their life. Most actually go off and do great things in the industry and generate value to society. But maybe that training is inefficient compared to a laser lab, a smaller laser lab, for example, and training 1,000 people in 1,000 laser labs rather than 1,000 people in one big lab. So that is something to study by economists. Opportunity costs of other science investments. I'll go down here, unreliability of international partners. So that's mostly other countries saying that about the US, but every once in a while the US can say that about other countries. And citizen relations. When the LHC turned on, there was a lot of citizen fear that a black hole would swallow up the Earth and the universe, and we'd all die instantly when the LHC turned on. Those fears were not well founded. Power line fears, neutrino flux fears, etc. So there's potential costs in all of that. So ultimately, Congress decides in the US and other places have different decision making. But by decision time, there are many experts who have weighed in and necessarily have weighed in, and sometimes physicists don't even talk to any of these people on the second and third categories. So particle physicists, accelerator physicists, other subfields of physics, even historians and philosophers of science, they have some impact in discussions with decision makers on this. So for example, a history and philosophy of science question about this is, just because colliders did really well in the past in discovering and revolutionizing our understanding of physics, what makes you think it will do well in the future? It's the past is not necessarily prologue question. And that becomes somewhat of a philosophical and historical question. And the answer, I think, is a very good answer for collider physics. And that answer, nevertheless, it needs to be addressed. So computer scientists, engineers, civil engineers, and then very important among the decision makers is the input from labor economists, cost-benefit analysis economists, social scientists, political scientists, local political leaders, national political leaders, and civics groups, all combine for a very complex juggling act of deciding whether or not all of these issues come together and speak to us by saying that it's of value to do it. And it's a hard decision, really hard decision. So the key complication is that different groups have very different key values they are after. So particle physicists, it's discovery of new physics. That's what we were born to do, and that's what we want to do. Keeping the field vibrant, training, and so on. Computer scientists are very intrigued by the computational and data analysis aspects. The politician is very worried about and cognizant of economic well-being issues of their constituency. Visible success is important, and the need to follow constituent values and desires. And the citizens generally fall into the category of an intense interest in knowing who and what we are, which revolutions in the understanding of nature speak to that, combined with a deep sensitivity of taxpayer stewardship. Does this really, citizens have the desire to have a strong STEM workforce that keeps innovation going and gives security? So, conclusion. We all know that it's not just about science when deciding on investing in very large-scale, high-impact endeavors, scientific endeavors. Any big science endeavor is, in my view, and I think history bears this out to some degree, is unstable and unsupportable over time that does not address head-on the comprehensive answer to the core value question. Does the activity increase value overall to the well-being of citizens? There's no unique answer to that question. Therefore, there will be differences of opinions. It's just a guarantee that that will happen. But somebody has to answer it, and it has to be a full-on discussion about it. Political leaders should be, they are the final say, and they should be the final say on public investment like this, not scientists alone, because it is their job and it is their responsibility to judiciously weigh all of these elements of the so-called core value question. So scientists must be humble enough to recognize that although their role is really vital in this, it is also limited. So I'll end with that. Thanks.
Well, thank you very much for that very thoughtful and informative and different approach. We have some questions. Some questions have come in online, and we'll be also seeing if we have questions here from the audience in the auditorium. So I'm going to try to separate these into missile defense and then collider physics/construction. And some of these questions came in earlier, and you, in a way, at least mentioned them, but we'll ask you to expound. So the first one is about the supersonic or hypersonic cruise missiles and how it is that physicists and engineers would approach defending the development of such a weapon.
Those, so let me make a comment about the challenge of it. So this is the so-called hypersonic glide vehicle. So an ICBM might launch, and it goes up high, and then it comes down, and it's ballistic. It's got maybe 280 seconds, 5 minutes of burn time at the beginning, and then the engines just go off, and then it's ballistic, the missile, and it goes up in space, and then it comes down and hits somewhere. The hypersonic glide vehicles, the challenge with that is that they can go into sort of an orbit, and then can travel a long distance, and then have the ability to maneuver in the atmosphere and go to a specific target at the end. So one of the key issues right now is that radar is very much geared towards missiles coming from the north, because if you launch from North Korea towards the US and you want to get it there within the ICBM's range, so the Hwasong-15 has a range of maybe 12,000 kilometers, it needs to come from the north. And actually it goes straight over Chinese and Russian territory, comes over the north, comes over Alaska. That's why we built this ground-based missile defense system is in Alaska. And it comes down, and it would come down towards continental US from there. With the hypersonic glide vehicles, it can go in any direction. It can go from the south and sort of go in orbit, and we don't have really good radar coverage down there. And so the first thing is, the very first step is to know that it's happening. So we have to have more coverage coming from the south. And how you defend against it is, well, I'm afraid it'll be too long of an answer, but it's basically really hard. And the second answer to that question is, we might not want to try to, given the reasons that I stated earlier. Oh, can I make one last comment about that? So they say hypersonic glide vehicle, and hypersonic sounds really scary. However, it's actually a lot slower than an ICBM, a fair amount slower. So an ICBM is something like 18 times to 20 times faster than the speed of sound. But these hypersonic glide vehicles are about 5 times the speed of sound. And that is a method by which it becomes easier. If you really wanted to do it. First of all, you have to know it's coming, so you've got to get your radar set up, and then you have to have batteries set up against something that's slower. Yep.
Okay, so this may be a suggestion. So are there other defenses than kinetic kill? For example, massive electromagnetic pulse surges, et cetera, that one might consider?
Yeah, so interesting question. Yeah, and there's constant development on that, but the director of the Missile Defense Agency announced last year or the year before that they were not pursuing that high power lasers. And the reason why is because, actually it was in the Missile Defense Review, that was, if you read the Missile Defense Review, which is public, you will see that that is mentioned as a possibility. But then later, the agency director said that they were not really pursuing that at this moment. And one of the problems is that it's hard to keep a focused beam for the distances that you need with high power right on the missile. So they don't view it as, at the present, as the best approach.
A kind of specific question about, I don't know if it's collateral damage, but what about detecting something that's not the threat, you know, false detection, say a commercial airliner or something?
Tragic example of that in our past, on an airliner, shooting down an airliner on a very short-range missile threat. Yeah, no, that makes it extremely difficult, and you know, if something launches and then it goes up to 1,100 kilometers, you know it's not an airplane, so that helps. But yeah, no, that's a serious worry, and it's a technical question, yeah.
So here's a question. Are there still what one might call go-to scientists? So there are committees like yours that you've served on, and probably many, but how is it that sort of either individual scientists or people with significant impact are in the process now?
It's a funny, when I was a postdoc at Stanford, one of the faculty told me that just after the war, World War II, that there were a couple of scientists who were involved with the Manhattan Project, where I think his words were, if they took a wheelbarrow up to Washington, D.C., the politicians would just fill it with cash for them, because they were viewed as so important. Nowadays, and rightfully so, in my view, there is no one go-to person, and I think that is good. But people have, I think it's probably more societies have respect. So scientific societies, I think the AAAS, the National Academies of Science, the American Academies of Science, the American Physical Society. I think when societies weigh in, they know that it's a large group of people who have thought about it a lot, and it's not just one individual's view of how the world should work. And that carries a whole lot more weight in today's world than individuals did back in the 1950s.
So we're going to move, maybe transition before we get specifically to collider questions, to maybe core value questions, a few of them. So one of them is, does a one-party country like China have a longer political or strategic planning horizon than the U.S.? And is that just an example of a different core value, or is there actually
But maybe it's better for me to answer that with respect to the American system. You know, China has certain policies spoken to the U.S. that have been consistent for many, many years. And that consistency, and the Americans have had their policies towards China that have been consistent for many, many years. What changes overnight is when a small action happens that seems to violate that policy, or a small statement might be said that seems to violate that the longstanding policy. But it's remarkably coherent strategic policies between the United States, Russia, and China for a long, long time. So I think both are pretty stable in this regard.
Comment on the latency? There are a couple of related questions. The latency from research to many of the potential impacts. And so you talked about training, which probably is a little bit immediate, and then there are very long-term things.
Yes. So so this is a tech transfer question, and how well can a new collider parlay into something really good for the business world industrially? And there, it's a long lead time. So the thing that we have to keep in mind is the people who are trained to do really well at the science at particle colliders are the people who are generally not trained well to understand how it can connect to the business world sort of overnight. It's very hard to make that connection. But in recent years, I think on the computational side, that connection has become more transparent. So there is a deepening road between particle physics and big data and artificial intelligence. And I think that one of the biggest values that is coming out of CERN and collider physics programs and Fermilab is this connection to top-level computing and industry. And many of the leaders in industry have come out of the particle physics background because it's a unique environment. There's just more data than anybody ever thought they would know how to deal with. And so now, most people, when they ask that question, they're thinking of a specific widget. Are we going to get a new microwave oven out of what happened at CERN, or a new different kind of airplane, or something very tangible? And the tangible things are much longer leeway, much longer lead time to that. And I'm not competent to know what might come out of that, but I feel confident enough to tell you on the computing side, it pays off every day.
This just goes on about things that have had impact over time. I'm thinking about superconducting magnets, which of course are key in medicine now with magnetic resonance imaging, and just every example of imaging came from physics, for example. Just one example. Okay. So one thing about, we're now going to move to the collider questions, I guess. And so one point is that these are international collaborations that include our military adversaries, China, Russia, and so on. So how would you assess that impact and include that in the bringing the world together at the same time that we have enemies?
So it's one of the core values that particle physicists have as international open science. It's a standard value, and it might be a selection bias, so to speak, because if you're not in favor of working with people internationally, you're very unlikely to go into particle physics, because your collaborators are from everywhere, and you go to CERN, and there's, I don't know how many nations are there. Same with Fermilab, citizens from different places. And it is deeply part of the particle physics community that it should be international and it should be open. So open science and international. There are a few people who might not like that aspect of it. I'm aware of a few people. I've met them in Washington and other places. But the good news is that we gain just as much from the international cooperation as others gain from us cooperating in this very open, forefront, non-military application science. So we gain tremendously by people coming out from outside of America with their insights and their work and their innovations. So it goes both directions, I think, very nicely. So I don't think there's any issue about international collaboration in particle physics experiments at all, and I think there's only positives in the way it's constructed right now.
We be concerned about a brain drain, that is to say, with the biggest experiments being not in the United States, that our best and brightest scientists will be going away from the United States?
Yes, it's a bit, when you have a hub, say CERN, for example, and a lot of scientists go to CERN, and it's the forefront thing, and they're attracted to it, then there's this prospect of them staying. So they go there for their PhD or postdocs, and they work on the collider, and there's this prospect of them staying. Certainly Europe benefits. I think it's unquestioned that Europe benefits from the state-of-the-art collider, CERN, economically, not just intellectually. So intellectually, that's for sure, they benefit from it. But even economically, I think it's fairly certain, given the economists that I have spoken to, that it's a plus economically. And part of that plus economically is retaining foreigners in Europe to do work and innovate in their business sector, and work for Airbus and work for other companies. And the more we have near us, the better we are going to be economically and intellectually. And so this is not necessarily a conflict that one would have between different regions, is that there's no reason that multiple regions cannot also be top-notch scientifically. And I hope that the US sees that benefit, that the decision makers see that benefit. But yes, there is a risk.
Now we're going to move to a few money questions. So the first question is, how much is really a lot of money to spend on an accelerator? $10 to $20 billion. We've heard amounts, of trillions lately being spent.
I told one of my students the other day that I'm old enough to know when $1 billion was a lot of money, and they said, "Oh, well." So yeah, you're right. If you look at it, several years ago, I used to give a talk about future colliders, and I showed there was a freeway butterfly system in the Midwest somewhere, and the total price tag was something like $4.5 billion. So how a bunch of freeways come in and they twirl around. You've seen them in some of these cities. They twirl around, and there's on-off ramps, And it's all done in concrete and bridges and civil engineering and all that. And this is on the tune of several $billion. Couldn't believe it. Several $billion. It's this, you know, to build a collider is several $billion. So, so at the same time, you know, but my economist friends, and I'm working with economists some, my economist friends, they press upon me that you can't think that way. The only way you're supposed to think is, does this investment make sense? That's how you're supposed to think. Does it have value? And if it doesn't have value, it doesn't matter if it's cheap compared to a butterfly freeway in Milwaukee. So there's going to be people, you know, economists spend a year determining the precise dollar amount gained in the Milwaukee metropolitan region by having this butterfly system of freeways set up. And they do the cost, and they do the salaries, they do the this, they do the maintenance, they do, you know, how much time do you sit in your car being unproductive? That actually counts. There's a number to that. There's actually a number that they give to your life. It was shocking. I forgot how many millions of dollars it were worth. But you know, there's a certain, you know, there's a reduction in traffic accidents. That counts for, I don't know, $5 million per life gained. There's a number to it. So everything, so not everything is economics. We have this issue of, do we want to learn? You're not going to learn the fundamental laws of the universe in Milwaukee on the freeway. So that's, you don't gain from that part. But how do you put a dollar value on that? That's extremely difficult to put a dollar value on that, but people try. Yeah. So we can't do comparisons. We have to ask, does this investment have value, and make the argument that it has a lot of value to citizens. And I think this is a mistake that physicists make, by the way. It's a mistake that I used to make. When I say physicists making mistakes, I mean I used to make this mistake. I would say, look, this collider doesn't cost any more than a little butterfly freeway system in the Midwest somewhere. And I thought that was a really good argument. It's not a good argument. So value, that's everything.
So in terms of funding this, the basic context has been government funding, maybe because it's so much money, but a lot of science has been funded privately, even physics-related science, I think, and certainly in medicine. So the question is, what's the prospect for that in particle physics?
Well, we have funding from the Simons Foundation on many things that overlap with particle physics, especially in theoretical particle physics. So theoretical physics is small potatoes financially compared to the big experiments. Nevertheless, a privately funded work is tremendous value, big leverage. And the Lion-Weber Center for Theoretical Physics is in the same category. Tremendous leverage on from private funding to enable scientific research. So, so usually private funders have a really good sense of where they can make good impact. And in these two examples, I think these are really two good examples. In the $20 billion realm, so there I think it's it's unlikely to see a collider be built, but going to Mars or a space trip or things like that, we've seen that people will do that. But there are ways to really make a big difference that the public investment is not quite understanding and not quite getting right, that the private persons come in and do it. In the case of the Simons Foundation, it was formal, long-term mathematical research that the government sometimes doesn't have as easy of a time knowing how to justify. So his value system, combined with a very careful analysis of what the landscape was, made a big impact in science.
This is specifically in mathematics and theoretical physics as opposed to experimental. Right. Okay, so there's also been questions about, what's more important, particle physics or something else, which I think maybe there's just a general answer that is it's all important.
I think this is a question. This is a question that has a possible answer to it. So not the which one's more important, but what presupposes that question is should we support it and at what level? So that's what presupposes it, because if one person is in their basement and says, I think this field is really important, it's not going to make much difference. But one can do analysis of this. And I mentioned it briefly, things like what attracts young people to physics? So if you have a field that is, there's many different values that a field can have. Some fields, their value is that there's tech transfer almost immediately. So it's closer to an engineering side. There's some fields where you draw in more people. And there's some fields where the society really wants to know. And, we've all been involved with, Saturday morning physics and the public. And the public is the energy by which all science happens. And the energy from the public has a non-trivial, a significant impact on scientific directions. And I think the public understands and knows that the questions of what are we really made of are questions that we universally are interested in knowing about. What is the fundamental constituents of what's inside my body? If I go deep, smaller and smaller and smaller and smaller distance scales, you're not going to know that without a particle collider. So the energy from the public, plus the economic arguments, plus the personnel arguments, these are all susceptible to analysis, and it should be continuous analysis for public investment. Taxpayer stewardship is not something to worry about. It's something to embrace, I think.
Okay, well, great. So thank you very much, everybody, for the wonderful questions that came both from the audience here and from those at home. And thank you so much, James, for that really fascinating and thought-provoking discussion and lecture today.